Good day. I am here to discuss about recursion tree. So what is a recursion tree? Recursion tree is useful for visualizing what happens when a recurrence is iterated. It diagrams the tree of recursive calls and the amount of work done at each call. Consider this recurrence t of n is equals to 2t of n over 2 plus n squared. And the recursion tree for this recurrence is this. In this case, it is straightforward to sum across each row of the tree to obtain the total work done at each given level. In this recursion tree, it has 4 levels. For the first row, it is the level of work done in the first row is n squared, while in the second row, it represents n squared over 2, while in the third row, n squared over 4, and for the last row, n squared over 8. Geometric series, thus the limit, the sum is O of n squared. The depth of the tree, in this case, that does not really matter. The amount of work done in the tree in each level is decreasing so quickly that the total is only a constant factor than the root. Recursion trees can be useful for gaining intuition about the closed form of recurrence, but they are not a proof. And in fact, it is easy to get the wrong answer with a recursion tree in the case with any method that includes. A good way of establishing a closed form for a recurrence is to make educated guess, then prove by induction that your guess is indeed in solution. Recurrence trees can be a good method of guessing.
Okay, so today we're going to talk about the master method, which is a method used in forming a recursion in a recursion tree. Now, what's a master method about? Okay. The master method is a cookbook method for solving recurrences. Although it cannot solve all recurrences, it is nevertheless very handy for dealing with many recurrences seen in practice. So basically it is handy, but we can't really rely on it. It's not that handy, not very handy. Suppose you have a recurrence of the form t of n is equal to at of n over b plus f of n, which a and b are both arbitrary constants and f is some function of n. This recurrence would arise in the analysis of a recursive algorithm that for large inputs of size n breaks the input up into a subproblems, each of size n over b, recursively solves the subproblems, then recombines the results. The work to split the problem into subproblems and recombine the results is f of n.
Okay, today we will talk about the yet another sorting algorithm. The following function sorts the first two-thirds of a list, then the second two-thirds, then the first two-thirds again. As you can see in this algorithm, here, take AM is the list consisting of the first elements of A, and drop AM is the list consisting of all but the first elements of A. Perhaps surprisingly, this algorithm does sort the list. We leave the proof that it sorts correctly as an exercise. The key is to observe that the first two passes ensure that the last third of the list contains the correct elements in the correct order. We can derive the running time of the algorithm from its recurrence using the master method. The routine does O of n work in addition to 3 recursive calls on lists of length 2n over 3. Therefore, its recurrence is t of n is equal to cn plus 3t of 2n over 3. If we apply the master method to the sort tree algorithm, we see that we are in case 1. So the algorithm is O of n raised to log 3 over 2 raised to 3 is equal to O of n raised to 2.71, making it even slower than the insertion sort. Note that being in case 1 means that improving f of n will not improve the overall time. For instance, replacing lists with arrays improves f of n to constant from linear time, but the overall asymptotic complexity is still O of n raised to 2.71.